Hey everyone, so today we're gonna dive into something super interesting topic, which is CMOS technology. You have probably heard the term CMOS before, right? It is literally everywhere, inside your phone, your laptop, your camera sensors, and even microprocessors. But what exactly is it, and why is it such a big deal in electronics? Well, that's what this video is all about, understanding how CMOS actually works layer by layer. So we have broken it down into three parts to make it easier to follow. First, we will go through the 3D structure of CMOS, where we will see how the NMOS and PMOS transistors are placed side by side on the same chip and how the whole thing comes together in 3 dimensions. Then we will look at the layers in CMOS, the different materials stacked together that make up the device, like the silicon substrate, the oxide insulation, and the metal interconnects. And finally, we will look at the fabrication process, basically how a CMOS chip is made from a plain silicon wafer to be an actual working transistor. But first, let's start with the basic. What exactly is CMOS technology? So CMOS stands for Complementary Metal Oxide Semiconductor. It is one of the most widely used semiconductor technology in the world, basically the backbone of modern electronics. It is the technology that powers everything from microprocessors and memory chips to camera sensors and even the logic circuits in your smartphone. What makes CMOS so special is how it uses two types of transistor, an N-type and a P-type. These two work in opposite phases. When one is on, the other is off. And that's what makes CMOS is incredibly energy efficient. Because of that, CMOS circuits can pack millions or even billions of transistors into a single chip, with very low power consumption when idle. In short, CMOS is the reason our modern devices can be fast, compact, and power efficient all at once. So here we've got two transistors, an NMOS and PMOS. The NMOS transistor conducts when the gate voltage is high, meaning when there is a positive voltage at the gate terminal, electron can flow from the source to the drain. On the other hand, the PMOS transistor does the exact opposite. It conducts when the gate voltage is low, so when the gate is at 0 volts, holes flow through the channel. And the really cool part is this, when one transistor is on, the other is off. That's where the word complementary comes from. Both transistors work in opposite phases. This complementary action means that there is almost no direct current path between the supply and the ground during steady operation. In other words, CMOS circuits draw very little static power, which is why they are super efficient. So if you think about it, this simple pairing of NMOS and PMOS transistor is what makes the entire CMOS logic family, including the inverters, NAND and NOR, so powerful and energy efficient. Alright, now let's take a look at how everything comes together, the 3D structure of CMOS. So CMOS basically integrates both NMOS and PMOS transistor on single silicon wafer. In the figure you can see on the left, we've got the PMOS transistor formed inside an N well, and on the right, the NMOS transistor built directly in the P-type substrate. You can see how the red polysilicon lines, that's the gate material, cross over the diffusion regions, and the gate voltage here controls whether the current flows through the channel underneath. And just below the gate, there is super thin layer of silicon dioxide. This acts as an insulation. It's what separates the gate from the channel and allows the device to operate based on the electric field, not direct contact. Then on top, we have a metal one which connects the source, drain and gate terminals. That's how the individual transistors are wired up to form circuits. The cool thing about this view is how it shows the designs of three perspectives. The top view shows the layer pattern, the layout pattern. The 3D view shows the full device structure, and the side view shows the internal layering from the substrate all the way up to the metal contacts. So this 3D model basically gives us a full picture of how CMOS devices are physically stacked and connected, turning a flat circuit design into an actual working chip. And that's what makes CMOS technology so powerful. Compact design, high performance and incredible energy efficiency, all built from this tiny complementary transistor working together.
Hello, I am Chibun. Now, I will be explaining the 8 typical layers used in a CMOS IC. These layers are built up from the base to form the transistor and wires that make up a modern microchips. The first layer is substrate layer, which base layer of P-type silicon that supports all other structures in the IC. Second layer, well layer. P-well and N-well regions used to form NMOS and PMOS transistor within the same substrates. The third layer, gate oxide layer, a thin insulating silicon oxide layers separating the gate from the channel controlling current flow. The fourth layer, polysilicon layer or gate layer, form the transistor gate electrons. Voltage here regulates currents between source and drain. The fifth layer, source or drain diffusion layer, heavily doped N plus and P plus region forming the current entry and exit terminal of the transistor. The sixth layer, silicide layer, a conductive layer that reduces contact resistance between silicons and metal connections. The seventh layer, metal layer, which provides interconnections between transistor and circuit components, may exist in multiple levels. And the last layer, terminal of NMOS and PMOS, which contact points of connecting each resistor to the external circuit, forming CMOS logic function.
Next, let's dive into how CMOS is fabricated. Firstly, step 1, which is substrate. The process begins with a clean, polished P-type silicon wafer, and this wafer acts as the base material for building CMOS transistor. Next, step 2, which is oxidation. A thin layer of silicon dioxide is grown on the wafer surface through thermal oxidation. It serves as a protective and masking layer. Step 3 is a photoresist. A light-sensitive photoresist is applied on top of the oxide layer, and this will allow pattern transfer during photolithography process. Step 4 is photolithography, which is UV light is projected through a pattern mask to expose selected region of the photoresist, defining the areas to be etched or daubed. Step 5, removal of unexposed photoresist. Mask is removed and unexposed region of photoresist is dissolved by chemicals such as trichloroethylene. Step 6 is etching. Hydrofluoric acid is added, which removes the oxides from areas where the dopants are to be diffused. Next is doping, which is ion implantation introduce dopant atoms like boron or phosphorus into specific region to create N-well areas for NMOS transistor. Next is polysilicon deposition, which is step 8. A layer of polysilicon is deposited and patterned to form the gate electrode, which controls current flow between source and drain. After that, the formation of gate region. The unwanted polysilicon and tin oxide underneath are then etched away. This gate structure acts the control terminal of the transistor and serves as a mask for the upcoming source and drain doping system. Step 10 is source or drain doping. Using the gate as a mask, heavily doped N plus and P plus region are formed beside the gate to create the source and drain terminals. Next step is metallization. Metal layers, usually aluminum or copper, are deposited and patterned to interconnect the transistors and form the circuit. In the diagram, shown that removing excess metal is removed. Next step is the formation of terminals, which is we can see that in the diagram form for interconnection in gaps are removed. Lastly, step 14, assigning terminal names. Names are assigned for terminals of NMOS and PMOS transistor. In summary, CMOS technology is essential in modern electronics because it offers low power use and high efficiency. The 3D structures show how NMOS and PMOS transistors work together to form logic circuits. The layers such as substrate, oxide, polysilicon, and metal each have an important role in building the device. The fabrication process involves several key steps like oxidation, photolithography, doping, and metallization to create the final chip. Overall, CMOS combines materials and advanced process to produce compact and reliable electronic device. Thank you.